Hello guys, welcome back to Simply AI. And today we will learn about something super cool called locally weighted regression. As you can get by the title of this video, this algorithm is going to predict a stock market price for short term. Basically, we want our model to zoom in and look for the nearby data when making stock predictions or stock price predictions. So for example, suppose if you want to make linear regression model for stock prediction, but not for the year or for the month, but for the specific week or a day or two. How will we do this? How will we only focus on the nearby data for short-term predictions? By the time this video wraps up, you're going to have every single one of them answered. So don't skip this. Stick with us till the end, and you will be walking away with all the answer you're looking for. But before we jump in, quick reminder, we have already cracked the code on linear regression and had learned about probabilities in our previous videos. So if you don't understand something in this video, you might want to go back to those previous episodes and join the fun. I will provide links to the video in the description as well. So let's quickly move on to our today's topic, which is locally weighted regression. So by definition, you can say it's a algorithm which is only focused on the locally data or the nearby data. We don't consider the complete data set. And why don't we consider the complete data set? We are going to discuss that. So just to understand, consider if we have data like this, right? So if we have data like this and we find out, okay, this is our hypothesis, which is the linear y equals to theta 0 plus theta 1 x. And we can see that this line is not the best fit. There are few data points which are far from this line, like this and this one. So suppose if we take our hypothesis squared function, or we can say we or we can say if we add x squared feature, our hypothesis will look like this, and we will say it's better hypothesis than previous one. And our hypothesis equation is going to be theta 0 plus theta 1 x plus theta 2 x squared, right? Now, if we increase our features, means if we take the fifth order polynomial or sixth order polynomial instead of the second order polynomial, what is going to happen? It will look like this. So it will go through all the points. So if you will see in this graph, the loss is almost zero. But is it good for the prediction? No. And why this is not good for prediction and why the first one is not good for prediction and the second one is the better choice, we're going to learn about this later. My point of showing you this is it's not always true that you take the higher order polynomial and you can say, okay, my model is going to be better than the previous one. No, even if you will take the higher order polynomial, it might not be the better model. So, what to take for hypothesis? We are going to discuss that later. But right now, the conclusion is the number of features matters, right? And the first case we usually refer as a underfitting. And the last one, where it goes through all the points, we say that this is the overfitting. And this middle one, we will say this is what we want. This is the model we will use for prediction. Because this is not the underfitting, this is not the overfitting. Okay, so I think this is a thing I have already told you. So choice of feature is important to ensure good performance. And how to choose features, we are going to discuss that later, but not on this video. Okay, so we all know these equations. These equations are from our linear regression video, right? So yi minus theta t x is the our loss function, is squared loss function, and theta transpose x is our output function. In locally weighted regression, only the difference is we are just going to multiply our loss via weight. So this weight is going to be non-negative value and it will be between 0 to 1. For the data where we want to focus, the weight of those data points is going to be near to 1. And the data which we do not want to focus and we want to avoid, the weight for those data is going to be near to 0. And we will just multiply that. So since it will be near to 0, the loss for those data is going to be 0 and it will those points are not going to contribute. Now, whatever I say, it might not make sense to you right now, but we will see how this is happening. You just remember it's exactly same as our linear regression. The only thing we are going to do, we are multiplying it by weight. Okay, so let's move on and find out what's weight here. The data I was discussing about is this. Okay, for this kind of data, no matter what feature you choose, whether it's a linear or a square or the fifth degree polynomial or the n degree polynomial, it's very difficult to find out the model for data like this. But suppose since we have already learned the linear regression, so we will just compare the locally weighted regression to the linear regression.
So the concept of locally weighted regression can be applied to other algorithms beyond linear regression as well. Okay, so locally weighted regression involves assigning different weights to data points based on their proximity to a target point. And what does it mean by? We will understand in this video. It's not only for linear regression. You can apply this technique to any other algorithm as well. Like when we study about the KNN and few other algorithms, we will see how locally weighted regression works there.
Suppose we want to predict the value for x equals to 17. So right now it's about 4.2, 4.3, but we want to make the prediction model for nearby values, which is like 15 to 20 or nearby values of the 17. So the first thing which we have already learned, we are going to implement linear regression in this data set, right? So use linear regression, and once we will use linear regression, our hypothesis will look like this, right? And so our hypothesis is like this, and we can see this our data is kind of, is about 5.5, but our actual data is just 4.2. 4.2. Line is the best fit, but it's not satisfying most of the data. So we will say this is bad model. So how do we do that? So the concept is, why don't we use local data to train our model? So what we want to do, we just want to use the data from 12 to 22, or 13 to 23. We just want to the nearby data to train the model. We don't want to use all the data. Okay, and then use linear regression for those data only. So suppose if we are taking this and applying linear regression only on these data set, our line will be something like this, and we will say this line is good for the the predicting value for x equals to 17 and the all the nearby data set. So maybe not good for all the data, but good for nearby input data, and that is what our task is. We do not want to, we do not want to create the model for all the data. We just want to create the model for local data prediction. We do not want to predict for the entire um, input range. So how to consider only nearby data and avoid all the furthest data points? That is our next task. So let's find out how do we do that. So let's clean up the graph and think about it. Our attention point is x equals to 17, and somehow we want to consider only nearby data and we want to avoid all the furthest data points. Okay, so suppose if we are calculating xi minus x, where xi is varying from 0 to 25 and x is our attention point. So we can see that when it will be xi will be 17, right? It will be 0. And we can make the one observation that if xi minus x is small, we can say it's close to x. And when mod of xi minus x is big, then we will say it's far from x. And after then we know this is the exponential function graph. So we'll just pass this in this function, and we can say that this is the our the weight. And this is the standard choice of the weight, xi minus x whole square upon 2 tau square. And tau is just the bandwidth parameter. So when we implement this, we will play with tau and we will see how we are changing the tau. What is happening? These dotted lines are going to get closer, or going to get far from each other.
Okay, so this is our WI, and this is how we will write it for the in case of our data is in matrix, right? So we all know that if it is a x square in matrix, we write it as a x transpose into x. So let's move on to its implementation and quickly implement this. Okay, so I have already written the program. I will just go line by line. So first box is just importing all the libraries like NumPy, Matplot for plotting, and then random to generate the random value of theta initially. So let's simply execute this. So let's execute this one by one. And this is the sample data which I have plotted. So input is the value in x-axis and output is in y-axis. So I just took the random data for now, just to show that how it's going to, the create the model. Now here we are printing the save of input and output, and then using matplot library, we are just plotting this graph. I think you all are familiar with these codes, and if you are not, please go and watch my previous videos. So this is how it will look like. So the next step, what we are going to do, I'm just taking some random values. So here the first one is the theta 0, the second one is the theta 1, and we know that theta 0 is the value when x equals to 0. So I have taken it as a 10, and the minus is the negative slope. That is why the line is like this, right? So I have just taken the random values 10 and -1. You can take anything. You can take the 0, 0 also. With these lines, what I'm doing, I'm just plotting my hypothesis, initial hypothesis, and my graph as well. So since it's taking all the space, okay, so since it's plotting line from 0 to 25, and on when we are passing 25, the value is negative, and that is why this graph is getting compressed. Let me write one line of code where we are going to take the value of x from 0 to 25 and value of y from 1 to 8, or yeah, 1 to 8. Just let's try to plot. Okay, so this is how our initial hypothesis is going to be. Now this is our loss function, and as you know, what we are doing, we are just multiplying by w or weight to our loss function, and I have named that w as a attention here. So we are taking the input, and this is the like all the rows, and take the first column, because if you will see here, before passing the value, we are going to add one column which will have the value of 1, because that is what we have done in our previous videos also, right? So that the theta 0, x 0, and we are going to say the x 0 is 1, and that's why we are adding one column with all the ones. And attention point is for the second column, and that is why what we are doing, we are just taking the second column minus whatever the attention point is. We can pass the attention point 20 or 5 or 10, anything. And then this is upon tau. So here I have taken 0.05 is the value of 2 tau square, I think it was. And you can take anything. So value of tau square, I have taken 0.05. I will take 0.01 or 0.02, and I will show you how it's making difference. So now this is the same code where this is the temp and the loss is this, which is our squared loss. And this is the gradient, and we are returning the gradient loss and gradient both. And we are going to use this gradient uh, in our gradient descent algorithm. So let's execute this, and this is our initial loss, which is 3.97, and these are our initial gradient. Now, and these are our initial gradient. Now let's write the final code, which is our gradient descent algorithm. So this code is for the plotting, and this is the gradient descent algorithm we are writing. So this is the gradient descent algorithm we are writing. It's very simple. So what we are doing, we are just doing the theta equals to theta minus alpha into gradient, and before that we are passing uh, all the inputs to loss function, and we are getting the loss and gradient here. We are just printing loss here so that we can observe that loss is getting decreasing, and then we are using gradient descent to optimize the theta. Now here we are calling the gradient descent function, and we are passing our attention point is 20. That means we want to build the uh, linear regression model only for this data, this local data, not for the complete data. So let's just run this and find out what is happening. Okay, so if you will see, this was our initial line, right? And uh, after each iteration, this line is getting trained, it's getting trained, and this is our final line. So if you will see, this line is moving towards this data. Line is line is moving toward this data because our attention point is 20. So if we plot our final line, this will look like this, right? Since we have created model for 20, now you can see this line is the better fit for all the nearby data, which is near to 20. It might not be better for all the data, but it's good model for this attention point. Okay, I just want to show you one more thing. Uh, Initial level only. I will just write one thing. I will print attention, and what I will do, I will just see how the attention is changing. So if you will see here, we pass the attention point 20. So if you'll see, this value is 1. That means for this our x was 20. And you'll see all these values, all these values has the value of input, and all the further points are going to be 0. And suppose if we are just increasing, suppose if we are decreasing the tau and we made it as a 0.2. And let's run this again. And this is the result which we have got. So this is the one. And if you will see, this time we are considering less values. So if you will see, this is also 0. So when we are decreasing the tau, our range is also decreasing. And when we are increasing the tau, our range is getting increased. So this is how, the tau is, this is how tau is contributing to your locally weighted regression algorithm. So I will provide this code in my LinkedIn profile or in GitHub repo, and you guys can take a look to it. And this was very minor change to our linear regression algorithm. Now let's see how do we use this algorithm to stock price prediction or short-term stock price prediction. So I've taken this Sensex data for a year, and this is how it looks like. So you know, the one thing I just want to say that, see, we are the example which we are taking the linear regression algorithm for this. But linear regression algorithm is definitely not the best algorithm to predict the stock market price, right? Since we have learned just the linear regression algorithm, I am using that everywhere for now. But once we will learn about more advanced algorithm, we will use those algorithm in order to do all sort of things. But for now, let's talk about the linear regression algorithm. And suppose if your data look like this and you are implementing the linear regression algorithm on this data, our hypothesis will look like this. So you can see, this is the bad model, because for this data, your hypothesis saying your stock price will go up, but it went 0. So suppose, and at this point, you will take this hypothesis, and at this point of time, you will say, I need to invest more money, and you will be ending up losing all the money, because from this point the graph is getting decreased. So definitely linear regression is not the best algorithm for a stock market, stock price prediction. Okay, so doesn't make any sense. Very, very bad model. Now let's think about the locally weighted regression. Let's try locally weighted regression for this. So we know that locally weighted regression is only going to work for the short-term prediction. It's not going to work for the long-term prediction. So suppose we want to predict for this, or June, uh, somewhere the first week of June. So first, when we are going to predict for the first week of the June, and we will say this is our attention point, what do we want to do? We will just care about the nearby data. We will just care about this data and this data, right? We will not care about these all the data and even this next data. But suppose if next data didn't even come, we just want to the make prediction for this data. So we just want to, care about this local data, not all the data points. And if we will implement linear regression for only this data, our line will be like this. So linear regression model for particular retention point. And obviously the line which we have achieved here, it's not good for long-term prediction, but it is good for short-term prediction, right? So for this data, if you will say, you're going to predict for this point, you will say this prediction is pretty good than your previous model. So that is how we are going to use the locally weighted regression to predict short-term stock market price. Okay, so few question arises from here that is linear regression a good algorithm for stock price prediction? Definitely no, right? Now, second, can we use locally weighted regression for short-term prediction? Definitely yes. So here we are using the locally weighted linear regression for short-term prediction, but later on when we will study about other algorithms, other advanced algorithms, we will use this locally weighted concept and those other algorithms to make better short-term stock price prediction. And we will implement this and we will create the demo project for this also. So just stick with us and I think you will be able to do so in our next 5 to 10 videos. Now, are the concept of locally weighted regression applicable to other technique apart from linear regression? Yes. So as I have already mentioned this, that the locally weighted regression is not the particular algorithm. The locally weighted, treat it as a, the concept, and wherever you want to focus on the just the local data or the nearby data, you can use this locally weighted concept in, in any other algorithm, not only linear regression. So suppose if we will learn about the neural networks, but you just want to implement that neural network for, the local data or for the nearby data, you can use the locally weighted regression for that. So I'm going to end this video here. And as we wrap up today's video, you know how to make changes in your algorithm so that only local data gets picked, right? And you can also use this concept across the other machine learning algorithm. It's not limited to linear regression. So if you guys enjoyed this video, don't forget to like, share, and subscribe for more exciting content. And thanks for joining us. Stay curious, keep learning, and we will catch you in the next video. Happy exploring. Thank you.